So our mechanism is called the Wentworth quick return mechanism. Essentially, the reason it is called the Wentworth quick return is because when you turn on the actual mechanism itself, where the motor is powered, the radius at the very bottom at this point is smaller compared to when it is at the top, and due to that, it causes different accelerations at different points. So essentially, the disc itself has the same tangential velocity on the outer edge, but due to the radius difference of the actual bar, it leads to a different type of acceleration on both points. So we can actually demonstrate that real quick. As you can see, the left side seems to accelerate faster than the right side, and that has to do with the fact of the different radii itself.
Hello, I'm Perrin Bowder. Today I'm going to tell you about our design of the Whitworth quick return mechanism. So we knew that we were going to have different freestanding parts, so we had to design a base. And so going through the different parts, first things first, we have to have the motor, right? And the motor is attached to this spinning circle. And the circle is of a specific diameter that we calculated would give us about a little more than a G. And we gave ourselves a little bit of room, greater than a G, to account for the friction that would occur in our mechanism. So it's not exactly idealized to be a G. So we've got this circle of a specific radius, and it's rotating around, this bar is rotating around a pivot point down here, and the length of this bar determines the tangential velocity that we see on the actual slider up here. So there are a couple things that we had to design for. One of them was the radius of the circle, which I've explained, and another was the actual distance between the center of this circle and the pivot point. So we designed our bar to be a certain length to give us about the right velocity on the slider there. And then we've got these two stands so that our slider will actually move in one direction and not slide around.
In order to find the equations of motion for our mechanism, we first needed to analyze the motion of the flywheel itself. So the flywheel itself is located at a distance y0, and it has a bar attached to it, which is this long bar right here. That has a position that can be described as x2, y of 2, where y of 2 is constant, but x of 2 is constantly changing. So we want to find x of 2. By doing this, we first say that the position of this dot right here is x of t is equal to r cosine omega t, and y of t is r sine omega t, where the total distance in the vertical orientation is y total is equal to y0 plus y of t. From that, we wanted to see how the change of angle, how the angle changes over time, which can be characterized by saying tan alpha is equal to x2 over y2. x2 is equal to x of t, and y of 2 is equal to y total, where y total equals y0 plus y of t. X of 2 is equal to y2 tan alpha t, and from there we were able to find an equation for alpha t, which is arc tan x2 over y total, which is this right here. From that we can then say that x of 2 is equal to y2 tan alpha t, which then gives us x of 2 equals y2 tan arc cosine omega t divided by y0 plus r sine omega t, which thus simplifies to x of 2 t equals y2 arc cosine omega t divided by y0 plus r sine omega t. From there, we can just then find the velocity of the slider by differentiating x of 2, and then the acceleration of the slider by differentiating the velocity.